Hey folks, in this video we're going to cover 3.5 day 1, which talks about features of sinusoidal functions. First, we're going to look at the sine function. In 3.4 we developed this sinusoidal function using the unit circle values. And now we're going to take a closer look at some of its characteristics, starting with the midline. The midline is a horizontal line that goes halfway through between the minimum and the maximum values. So without any transformations, the midline of the sine function is at y equals 0. Next is the amplitude. The amplitude of this function is the distance from the midline to the maximum or the distance from the midline to the minimum. And in the parent function here of this sine function, that amplitude value is going to be 1. Next up is the period. The period length is the length of one cycle, how long it takes for that function to go through its wave before the values start to repeat. And in the parent function, our period is going to be 2 pi. The frequency is related to the period. The frequency is the reciprocal of the period. So that would be 1 over 2 pi. I think of it as one cycle repeating every 2 pi radians. Another important characteristic to notice is that this graph oscillates between concave up and concave down. So we have lots of points of inflection where that concavity is changing. We're going to look at the cosine function next. That's our second sinusoidal function. And we're going to be looking for these same features, starting with the midline. That again is this horizontal line that goes halfway through the minimum and the maximum values, so right through the center. For y equals cosine of theta or cosine of x, that midline is at y equals 0. The amplitude, again, is the distance between that midline and the maximum, or you can look at the distance between the midline and the minimum. That amplitude value for the cosine function is 1. Our period is going to be 2 pi. And then the frequency, the reciprocal of the period, is 1 over 2 pi. And just like with that sine wave, the cosine wave is going to alternate concavity between concave down and concave up. In 3.4, we talked about how the sine and cosine functions are horizontal shifts of one another. So you'll notice that the sine wave starts at the midline and the cosine wave starts at the maximum. So their y-intercepts are going to be at a different part of that wave. Our goal in 3.5 is to identify these characteristics for various sinusoidal functions that have been transformed. We're going to be focusing on graphs and verbal representations. Eventually we will add in tables and equations into the mix, but for now we're mostly going to be looking for these 4 features: period, frequency, midline, and amplitude from a graph or from a verbal description. So starting with a graph, we have 2 periods of a sinusoidal function, f, that are shown in this graph above. We are tasked with finding the period, frequency, amplitude, and midline for the graph. So I'm going to start with period and frequency. So I'm looking for the length of one cycle. I notice that this graph kind of starts at the midline, goes up, down to the minimum, and back up. Before I continue into the next cycle, I'm going to stop and notice that the period length here is pi radians. The frequency would be the reciprocal of that, 1 over pi. The midline is going to be the horizontal line that cuts that graph in half. Now the midline needs an equation. I see that the y value there is 3, so the equation for this midline would be y equals 3. Finally, the amplitude is the distance between the midline and the maximum, or the midline and the minimum. So thinking about what is that vertical distance. So I see our maximum is 6 and our minimum is 0. So the amplitude would be the distance between them, which is going to be 3 units. I would like you to try this one on the next slide. Pause the video, take a look at this graph of g, this sinusoidal function g, and identify the period, frequency, amplitude, and midline. Press play in the video when you're ready to check your answers. All right, this sinusoidal function started at a maximum. The next maximum happened at pi over 2 radians, so this period would be pi over 2. The frequency is going to be the reciprocal of that, 2 over pi. The midline is halfway between the minimum and the maximum at y equals 1. The amplitude was 2. There's 2 units between that midline and the maximum at 3. And also 2 units between the midline and the minimum at -1. All right, so next, instead of a graph, we're going to have a verbal description of a sinusoidal function. So this one says the sinusoidal function h has a maximum at the point pi comma 8. The first minimum after reaching that maximum occurs at the point 3 pi comma -2. And our task is to find the period, frequency, amplitude, and midline for this function h. I think the best way to find these features is to draw a quick sketch. So I'm going to draw my axes here, where my input is that angle in radians, and my output is going to be one of my ratios. It doesn't tell me whether it's sine or cosine, so I'm just going to call it h of theta. I'm going to plot those 2 points, starting with the maximum. Had an input of pi and an output of 8, so that'd be somewhere above that horizontal axis. And then our minimum happened later at 3 pi -2. Not really worried about the scale, just worried about making a general picture for my sketch here. So my sinusoidal wave would start from that maximum and head down towards the minimum. As far as the period, this does not show a full period. A full period would be back to a maximum. So here I have half of a period. If half of the period would be from pi to 3 pi, I can subtract 3 pi minus pi to find that that half period is 2 pi, which means the full period would be double that, 4 pi. The frequency is going to be the reciprocal of the period, so that's going to be 1 over 4 pi. The midline now is going to be halfway between the minimum and the maximum. To find that algebraically, you can find the average of the minimum and the maximum values. So if I take 8 plus -2 divided by 2, I can find what's halfway in between those 2 y values. So that'd be 6 over 2, which is going to be 3. So the midline equation is going to be y equals 3. Finally, our amplitude. Amplitude, again, is the distance between the extrema and that midline. So in my sketch, I'm going to add in approximately where this midline is at y equals 3. Again, my sketch was not to scale, but to just give myself a frame of reference, the amplitude now is going to be the distance between that midline and the maximum, or the midline and the minimum. So I can take 8 minus 3 to find that amplitude is 5. All right, for our last example, we're going to go back to FRQ3, and we're going to look at a scenario we've previously looked at. We're going to practice some of those same skills as we've been practicing throughout Unit 3, but we're going to add in some of these new features at the end. So the scenario we're going to look at is this clock that's mounted to the wall, where we're tracking the distance between the end of the minute hand and the ground over time. So starting with rereading the scenario and adding in some labels to this diagram, it says the figure shows a large clock mounted to a vertical wall. The clock has an 8-inch long moving minute hand, so I'm going to add that label in. The minute hand is 8 inches long, and the center of the clock is 120 inches directly above the floor, so I'm going to add that in too. And again, that's from the center of the clock to the ground. Next, it says that at time t0, the minute hand is pointed directly up, as shown in the figure. So this could be time 0 when that height is at a maximum. However, the clock is not working properly, and the minute hand is moving twice as fast as it should. So the next time the minute hand points directly up at the 12 is 30 minutes later, at time t equals 30. So this would also be time 30 in the picture. As the minute hand moves, the distance between the endpoint of the minute hand and the floor periodically decreases and increases. The periodic function h models the distance in inches between the endpoint of the minute hand and the floor as a function of time t in minutes. Our first task is going to be to determine possible coordinates t comma h of t for these 5 points. So I like to start with our vertical values, those y coordinates, looking at the maximum and the minimum distance this minute hand could be off the ground. So since the distance to the center of the clock is 120 and the clock hand is another 8 inches long, that maximum distance is going to be 128. If I take 120 minus 8, I can get the minimum height, which would be 112. And then the center of the clock, 120, would be that middle height, halfway between the minimum and the maximum. Now looking at time, I see that time 0 is when that minute hand is at a maximum height at the top. So 0 times 0 could be any maximum. For convenience, I'm going to make point F that maximum at time 0. It would complete that cycle 30 minutes later. So at the end of one period, we'd be at point P, which is going to be the time 30. Cutting that in half to get the time for point J, that would be 15 minutes, halfway through that cycle. Half of that would be point G, half of 15 is 7.5. So each of these increments between two consecutive points is going to be 7.5 minutes. So from J to K, I'd have another 7.5 minutes. So if we take 15 plus 7.5, we get 22.5. Now I have all of my values for both time and height for all 5 points. So starting with F, the coordinates would be 0, 128. G would be 7.5, 120. J at the minimum, halfway would be 15, 112. Back back up to K, 22.5, 120, and ending our period with P, 30, 128. Now that we've determined the coordinates, we're going to use them to find the period, frequency, amplitude, and midline for this function h. So I'm going to go ahead and copy down my values from the previous slide and label our input and output values. Alright, starting with the period, the length of one cycle, this would be from F to P here. We know that it takes 30 minutes, so our period is going to be 30, and the frequency is the reciprocal of that, 1/30. I'm going to do the midline next. The midline is that horizontal line that slices that sinusoidal wave in half. In an FRQ3, the midline is always going to be this dashed line. In the past, we've talked about how sometimes there's a false assumption that your midline is the x-axis. That could be true, but usually it's not a y value of 0. So here the midline is that middle height of 120. So our midline would be the equation y equals 120. Finally, our amplitude is the distance between that midline and our extrema, either the midline and the maximum or the midline and the minimum. So in our case, those values are 8 units apart, which is the length of the minute hand. So our amplitude is going to be 8. Lastly, we have an analysis of some features. It says find two intervals for which the graph of h is both decreasing and concave up. So my y values need to be getting more negative, but the slopes need to be getting more positive. So decreasing and concave up is going to look like this shape. So I see one interval between J and G. My next interval would happen to the right of the points that I have. So I do know one of my intervals right away. That would be 7.5 to 15, and I'm going to write that in interval notation. I need to extend my input axis, this t-axis, to find the values for the next interval. So remembering each of those kind of quarter waves was 7.5 units long. The next point that I would need for the start of that interval would be 37.5, and then the end of that interval, if I add 7.5 again, would be 45. So that next interval would be between 37.5 and 45. All right, that wraps up section 3.5. In the upcoming sections, we're going to add in equations into the mix, both starting with an equation and identifying these features off of that equation, and then ultimately being able to write our own equations for sinusoidal phenomena.